So we started off doing a lot of this last year at the very beginning. The very beginning stuff, sorry, is from last year, but we also add Radian Measure in right away. So instead of doing everything in degrees like we did last year, we're adding radians, which is another form of measurement. So standard position is when we sketch angles called rotation angles on the Cartesian plane, the XY axis, with the initial arm, where the angle starts at the positive x-axis. These angles can be positive, move counterclockwise, or negative, move clockwise. So last year you would have looked at positive ones. So what I'm going to do is I'm going to label it in degrees for now. So this would be 0 degrees. If it's positive, we go counterclockwise. Then this would be 90 degrees because it would make that little box. 180 degrees, 270 degrees, 360 degrees. And then it could keep going, couldn't it? I could have 450, 540, and it just could keep going on forever, right? They keep going around and around and around and around. So say I wanted it at 210. 210 is between 180 and 270, and it's 30 degrees more than 180. So remember, when you split the quadrant in half, it's 45. So 30 is a little less than half. So this would be my terminal arm. I'm going to call it terminal arm. And this would be my initial. And I have a circle here because it's rotating around the center. So this is my initial. So I start at 0 and I go to 210. If I don't actually put an arrow around these arrows to tell which direction I'm going, it could be a negative or a positive. So what I have to make sure I do is I start on this arm and I arrow around to this arm saying that it's counterclockwise, and then I label it 210 degrees. So you did positive angles last year. We're also looking into negative angles. So negative, you still have these arms, but we're going to start here, and this is going to be 0. And then we're going to go clockwise, and then they make negative angles. So this would be negative 90, negative 180, negative 270, negative 360. And then I could keep going, negative 450, negative 540, and just keep going around. Over and over and over, and keeps rotating, 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 right? So now if I did negative 210, my initial arm is still on the positive x-axis, so I'm always going to start. So this is my initial. But I'm wanting to go to negative 210. So now I'm going to be between negative 180 and 270 in this quadrant up here, and 30 more than negative 180. It needs to be 30 more. So then I rotate like this. It's negative 210. So the terminal arm is where the angle ends and in what quadrant. So another thing to note is your quadrants go like this. Top corner, 1, 2, 3, 4. I know, but so what angle correspond to each of the axes? We labeled them above. Okay, so what I would always suggest you do is when you draw the quadrant, the Cartesian plane, please label the axes as to what degrees they are. It makes your life a heck of a lot easier. I know it takes a bit more energy, but you'll make way less mistakes. So we need to sketch the following in standard position. So we're going to sketch 40. 40 is a positive angle, correct? So we're going to draw our Cartesian plane. And we're going to go counterclockwise, starting at 0, and label our axes. So 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. These all need to have little degree symbols. This one, you need to have a degree symbol. It should have. So, bless you. They have to have degree symbols or else they're not degrees or radians. And right now that means nothing to you. But what you need to take note of is if it doesn't have a degree symbol, it's a radian, which makes it totally different. So whenever you're saying degrees, you have to have a little degree symbol or it's not good. It's bad. Just take that from now. It's not good. Okay? So 40 would fall between 0 and 90. 45 is halfway through. So we're going to start with our little dot here. We're going to have our initial arm. And then we have to go up 40. So not completely splitting that quadrant in half. Just a little less. And then we label up. And we can say 40 degrees. You guys try B, C, and D. This is just a repeat of last year except for the negative. So 140 is positive, so we're going to label it positive. 0, 90, 180, 270, 360. So then we go to 140, which is 40 less than 180, so not completely halfway. And our initial arrow to it. Negative 240. We're going to label our axes counterclockwise, or sorry, clockwise. So 0, negative 90, negative 180, negative 270, negative 360. Negative 240 falls between negative 180 and 270. It's 30 less than 270. So I'm going to go up like that. Or I could say it's 60 more than 180. Either way, you still get to the same terminal arm. Negative 240. And then we have 340. $20 less than 340. If we don't arrow where it is, then we could be representing this little piece in here, which is negative 20. Is that the same as what I wanted? No. So I have to arrow around. However, negative 20 gets me the same terminal arm as 340, doesn't it? So negative 20 and 340 actually terminate on the same arm, which is something that's important to us later. Well, soon. Okay. Radian measure. There are two ways to measure angles. For you guys, radians are something that you guys are going to fight because since you're little, you've been taught degrees. If you had been taught radians your whole life, and then today was trying to tell you, and there's another measure that means the same thing and it's degrees, you'd be like, I'd rather pick radians. You just feel more comfortable with degrees because it's something that you've always dealt with, okay? But they get you the same thing. And the reason why we use radians is word problems make no sense in degrees. So what we're going to be dealing with later on is like rotating a Ferris wheel all the way around. And we'll say a Ferris wheel rotates every, you might say 300 degrees. And you'll be like, no, that's 360. A wheel rotates every 360. So it doesn't make any sense in degrees if you actually do word problems. So all word problems are always in radians. That's why we have to learn radians. Also, calculus is fully in radians. Radian measure is actually way better to use than degree measure is because it's more accurate for a lot of situations. So we're going to look here. This here is your 360. So say we did this, it would be 0, and we said 90, and then we said 180, and then we said 270, and then we said 360. We agree? The unit circle, which is what we're going to be using, has a radius of 1. So the circle itself has, that's actually not even, it's not great, but it could be way worse. Okay, it has a radius of 1. We agree? So what's the formula for a circumference of a circle going around the outside? If you need circumference, just use pi d. Okay. So pi d, or we could say 2 pi r. 2 pi radius, correct? Because the reason why is d is 2 r's, right? And then I just threw the pi in the middle because that's just the way they write it. Okay? So our unit circle has a radius of 1. So going around the outside of a unit circle, around the whole outside, we could say, hey, it's going to be 2 pi times 1. So it's 2 pi. So degrees-wise, it takes us 360 degrees to get around. Do we agree? But in radian measure, which is pi's, it actually takes 2 pi to get around. So 2 pi and 360 are besties. 2 pi is the radian measure, and 360 is the degree measure. Okay? So if 360 is 2 pi, what would 180 be besties with? If 360 is 2 pi, and it's 2 times the amount of 180, what would 180 be? Just pi. So 180 and pi are besties. Okay? So if we want to convert anything, we're going to use pi over 180, or we're going to use 180 over pi, depending on if we're going from degrees to radians, if we're going from radians to degrees. Okay? So this is the key thing here. To convert from radians, or degrees, sorry, to radians, pi's on top. So we say Dr. Pot. You're like, that's stupid. It doesn't matter. You will remember how to do it. So degrees to radians, rads, pi on top. Some people memorize the other one as RD Pob, or they just say, hey, it's the other way. Up to you. Radians to degrees, pi on bottom. So you're either going to multiply by pi over 180, or you're going to multiply by 180 over pi. Okay? It just flips depending on what you're finding. But if you're going from radians to degrees, pi's on the bottom. If you're going from degrees to radians, pi on top. Everyone remembers this one. Okay? So if we're going from degrees to radians, pi on top. So let's prove that 360 is actually 2 pi. So if I had 360 degrees, I would be going from degrees to radians, right? So degrees to radians, pi on top. So I'm going to multiply by pi over 180. We agree? So we're going to get 360 degrees pi over 180 degrees, if we really want to. The degrees cancel, and we're left with 2 pi. So 360 actually does equal 2 pi. Now, if I say 2 pi, that's assumed to be radians. So if there are no units, bless you, if there are no units, the units are rads, radians. So I can either say 2 pi, and we assume it to be radians. That's why we need the degree symbol in order to know that it's a degree. So I could say 2 pi, that's radians, or I could say 2 pi rads, or I could say 2 pi radians. These all mean the same thing. But if there is no unit behind it, we assume it to be a radian measure. Okay? That's why the degree symbol is super important. If you don't have the degree symbol, it's assumed to be a radian measure. So here it says when an angle is given in degrees, it must have the degree symbol given immediately after it. When it's measured in radians, the angle either has rads after it or nothing at all, or it could have the word radians. Okay? So we're going to go here. Convert from degrees to radians. Degrees to radians, pi on top. So are we going to multiply by pi over 180? Or are we going to multiply by 180 over pi? These are our questions. So we're going from degrees to radians. What are we going to multiply by? Degrees to radians, pi on top. So pi on top. So we're going to multiply by pi over 180. 270 is just over 1, correct? When we multiply fractions, we multiply top times top, bottom times bottom. So we're going to get 270 pi over 180. Converting between the two is going to be your best friend because you are going to be converting like crazy people throughout this entire unit. 270 over 180. You can take 90 out of both, and you get 3 pi over 2. So now we want to convert this one. And look at this. It says, give your answer as an exact value. That means not a decimal. So those of you on the test who, when I said exact values, gave me decimals, you actually gave me not what I wanted. Okay? Exact values are reduced radicals, or just not decimals, actually. Complete opposite of decimals. Okay. So 315 times pi over 180. We get 315 pi over 180, which equals what? 7 pi over 4? So why would they ever, for the second part, convert the following from degrees to radians to the nearest tenth? Why the heck would they ever ask us to the nearest tenth? Because nearest tenth means rounded, which means not as good as exact, which means not as accurate. Why the heck would we ever have to round to the nearest tenth? What do we have on our unit tests and on our diplomas? Numerical response. That is the only reason. Now, what they could do, though, instead of asking us to round to the nearest tenth, is they could say a pi over b, and then what's a plus b or a b and respectively, so you'd put them in that order. So then you wouldn't have to turn it to a tenth, right? You just tell me what's in front of the pi and what's at the bottom. So you can do that too. But we're going to go over how to do it to the nearest tenth just to make sure. So we're going to multiply by pi over 180. And so we get 70 pi over 180. If I want to the nearest tenth, I'm going to go 70 times pi divided by 180 into my calculator. So everyone try that out. What do you get to the nearest tenth? Remember, 10 has 1 0, so nearest tenth is 1 decimal place. However many zeros there are in the word tenth, hundredth, thousandth is how many decimal places. So tenth is 1 0, 1 decimal place. So what do we get? Make sure you put the pi in. If you don't put the pi in, you didn't actually give me the answer. What'd you get? 1.2? Everyone else? Yes? No? We agree? Okay. So you guys do 205. So we're going to multiply by pi over 180. We're going to type in 205 pi divided by 180. And what do we get to the nearest tenth? Pardon? Thank you. Okay, so that was degrees to radians. Now we're converting from radians to degrees. So RD-POB, if you want to remember it, radians, degrees, pi on bottom, or it's just the opposite of the other one. So pi on bottom. So we're going to go 180 over pi. What's great about this, if the radians actually has a pi in it, the pi's just cancel. Boom, boom. And I'm left with 180 divided by 4, which is 45. What do I need to remember to have? A degree symbol, or else it is actually radians. Next one, we're going to multiply by 180 over pi. The pi's cancel, which is a nice in this situation when they actually have pi's. What's negative 7 times 180 divided by 3? What do you get? Negative 7 times 180 divided by 3. Negative 420 degrees. Okay, what happens if they don't have the degree symbol? So convert the following from radians to degrees. So we still do the same thing, radians to degrees, pi on bottom. So we're going to multiply by 180 over pi. The problem here is that the pi just doesn't cancel, right? So we're going to type into our calculator 1.57 times 180 divided by pi. We actually have to have the pi into our calculator. And what do we get to the nearest tenth? 1 decimal place. Anyone? JC, did you get it? 40.0. So if there is no pi, you just have to remember to divide by it. No? What'd you get? Which one? Just 90? Okay, then we go negative 1.4 over 1 times 180 over pi. Then we get negative 1.4 times 180 divided by pi. And what do we get? Just type it in. Negative 80.2 degrees. All right? Okay. The next thing we do this lesson is kind of an alone lesson that just pops up all the time. We practice questions with it, but it's kind of a standalone little piece. I don't know why. But if you look at the right-hand side of your formula sheet, the entire right-hand side is trig. So chapters 4, 5, and 6 are this, okay? The people who are good at chapters 4, 5, and 6 know what's on this formula sheet. They don't go searching. They know what formulas are there. This next little lesson is going to use that very top formula that's kind of a standalone formula, okay? It's theta equals A over R. It's used when we actually are trying to find arc lengths. So they'll give us the radius of a circle. They'll give us the arc length, the outside of the circle, like how far apart it is from one radius to another radius. And then we can find the angle. Or they'll give us the angle and the radius and we have to find the arc length. So that's when we use this formula. A represents arc length. What the heck is an arc? Well, if I drew a circle like this, and I had this radius here, and this radius here, this would be the arc that joins it. So that there would be the A. Okay. R represents radius. These two have to be in the same unit. So if one's in meters, the other one has to be in meters. If one's in centimeters, the other one has to be in centimeters. Okay? This is your angle, and this is the key error that people make. This is your angle, so the angle in the middle. So for example, it could be this angle here, this theta, or it could be this angle. If it was this angle, the arc I would be looking at would be this arc. So if it was this angle here, the arc would be the arc that corresponds to the angle, okay? The key thing, this is where people make mistake, is that the angle needs to be in radians. This formula only works if you use radians. So if they give you degrees, you have to convert it to radians before you can use the actual formula, okay? People forget that. So how do they ask this question? They'll ask you to, they'll either give you this question in degrees, you have to convert to radians to be able to use the formula, or they'll make you find the angle in degrees. So when you actually find the angle using this formula, it gives you your answer in radians, and then you have to convert to degrees. Okay, so you're often having to convert either to use it or at the end to get the correct answer. So let's look at a question. A pendulum, 30 centimeters long. There's my pendulum. It's 30 centimeters long. Swings through an arc of 45 centimeters. Now it's over there. Pendulum got smaller somehow. I don't know. Through what angle does the pendulum swing? So they want this. Remember the arc that you're finding? The angle you're looking for is the angle that correlates to that arc. Answer in degrees and radians. Your answer that you're going to get from this formula is going to be in radians, correct? Then I'm going to have to convert to get it into degrees. So theta equals A over R. We're actually looking for theta, so we don't have to rearrange this formula. So we're going to get theta equals arc, which is 45 centimeters, divided by radius, which is 30 centimeters. And our units cancel, which is great, because radians has what units? No units, right? Like you can have a number without any units and it's radians. So theta equals what? What's 45 divided by 30? 1.5, I believe. So that's my radian answer. I can put rads behind it. But most often, if they'd ask you this question, they're going to ask for it in degrees. So radians to degrees what? Radians to degrees, pi on bottom, RDPOB, or Dr. Pot. RDPOB or Dr. Pot. So radians to degrees, pi on bottom. So I'm going to multiply by the pi on the bottom. So 180 is on the top. So you're going to go 1.5 times 180 divided by pi. And what do you get? Sorry? Degrees. Okay? The next one says, calculate the arc length. So they want you to find A. To the nearest tenth of a meter if the sector of the circle is a diameter of 9.2. Can I use diameter in this formula? What do I need to put? Radius. Radius is what? The diameter. Half of it. So 4.6. If the sector angle theta equals 150 degrees. So now I just plug it in. What's my problem? Theta needs to be in radians. Theta needs Theta needs to be in radians. Okay, or you can't plug it into this formula. I wish when you went to go plug it into the formula, it would just jump out of the formula if it wasn't radians. Like you'd write on your page and then it would just fly off. And you'd be like, what is going on? And you try to put it back and it would fly off again. Wouldn't that be great? Like you literally couldn't calculate it because your paper would make the radians, the degrees fly off your page. It'd be fantastic. Okay, so we want degrees to radians. Dr. Pot, degrees to radians, pi on top. So we're going to do 150 pi divided by 180. We can reduce the fraction. What does the fraction become? 5 pi over 6? But we don't want to put it into a terminating decimal. This is something you need to, I'm sure you've learned it in math before, but I'm going to remind you of it. When is the only time you can actually round a decimal? When you're done the question. The very last step. What happens if you round earlier? You'll have the wrong answer in a written response, or you might have like 6.2 in a numeric response, but the answer is 6.3. Will the little machine, when it flies through, be like, oh, you're close enough? No, the machine will be like, I am set to give answer for 6.3. You gave 6.2. Now, that's what it's going to do. Except it just does this, and it's through. Like, that's it. It has no heart. Okay? So, 5 pi divided by 6, if you actually typed that into your calculator, took the decimal, rounded it, and put it in, would that be okay? No. When are you allowed to round? Your very last answer. So if you went 5 pi divided by 6, you'd have to hold that in your calculator, that decimal, and keep working it through. I would not suggest that. I would just keep having the exact values as we go along. So theta equals A over R. Theta is 5 pi over 6 equals A over 4.6 meters. So what do I do? How do I get A by itself? Multiply by 4.6. So I'm going to get A equals 5 pi over 6 times 4.6 meters. So what is my arc length? 12.0? Don't forget units. If you have the unit of one of them, like the radius or the arc length, you have the unit of the other one because they have to be the same units. Did everyone get 12.0? Yeah? Okay. When you're done that, we're going to flip over. I did release these notes on Classroom yesterday. Okay. Key thing that we learned last year was we didn't learn coterminal angles. I'll deal with those in a second. We learned reference angles. Reference angles are the cute little angles that are between the terminal arm and the x-axis. So say I had 0, 90, 180. You need to label your axes, especially if it's a written response or you're in trouble, because it could be anything, right? If you don't label them, it could be positive, it could be negative, it could be larger, it could be smaller, right? You need to label your axes. So say I had 160. That's my angle in standard position, correct? My reference angle is always the little angle that falls between my terminal arm and the x-axis. So this one would be a reference angle of 20 degrees, because this right here, this little green angle, is 20. I always say that the reference angles are just the little bow tie angles. So if I drew a bow tie, if I drew terminal arms out of each quadrant, like this, if those were all my little terminal arms, this here would be my reference angle, this would be my reference angle, this would be my reference angle, that would be my reference angle, and they would make a little bow tie with the x-axis. So the reference angles are always the little angles between the terminal arms and the x-axis. And you learned that last year. So for each of these ones first, what we're going to do is we're actually going to draw them, and then we're going to do the reference angles, and then we'll do the coterminals after that. But for right now, we're just going to do the reference angles. So 60. We're going to draw it first. So you go 0 degrees, 90, 270, 360. 360. Whoa, I went up to lunch. 180, 270, 360. So I'm going to draw 60. 60 is 30 less than 90, so it'll be like here. Here. That's supposed to be right on the x-axis. And 60. Then I want the reference angle. Remember, the reference angle is the angle between the terminal arm and the x-axis. So the reference angle would actually be, here's my terminal arm, here's my x-axis. So here to here. So my reference angle would actually be 60. So anything in quadrant 1 has the same terminal angle as reference angle, because from terminal arm to the x-axis is the actual angle of that arm. You guys try 300. Draw it and see if you could possibly come up with the reference angle. Remember, it's from the terminal arm to the x-axis. Try 300. And then we're going to do the radian ones. So we label it positive, 0, 90, 180, 270, 360. 300 is 60 less than 360, or 30 more than 270, whichever way you want to go about it. And I have to arrow around, say it's 30 or 300. My goodness. And then the reference angle is from the terminal arm to the x-axis. So what would it be? 60. This is the key thing. Your reference angle is always positive. So we're going to go up here and we're going to say that too. Always positive. You might say, of course it's always positive. Well, where people think it's not positive is if I gave you a negative angle. So say down here, I don't know why it did this little weird wingding thing, but we'll ignore that. So say down here, I did negative 135 degrees. Okay, I'd go 0, I'd go negative 90, negative 180, negative 270, negative 360. 135 falls directly halfway between 180 and 90. It's 45 degrees. Less than 90, or less than 180, more than 90. It's be right up the middle. But the reference angle is how far away you are from the terminal arm to the x-axis. How far away, think of it as like a distance. Distance can't be negative. Okay? So how far away are we from this terminal arm to this x-axis? How many degrees? Just go 180 minus 135, right? Or how far away this is. Yeah, you just count to 180. So 180 minus 135 is how many degrees? 45. So it's a reference angle of 45 degrees. Not negative 45. Don't care that it was 45. Oh, so this was a negative angle, right? Reference angle is always positive. All right, then to radians, of which you have no idea what 5 pi over 3 is. So what we need to do first is we need to label our axes, just like we did before, but we have to label them in radians. Okay? So it's positive. We're going to go in a positive rotation. So we do 0 radians, and this is 90. Okay? So this would be 90 divided by 180. So it'd be pi over 2. Then this one is going to be 180 divided by 180. Add a pi. What's 180 divided by 180? 1. So it's just pi here. Then this one is going to be 270 divided by 180. What's 270 divided by 180? As a reduced fraction. 3 pi over 2. And then this one is what? 2 pi, because 2 pi and 360 are friends. Okay. So 5 pi over 3, really nice radian measure. Super awesome, okay? If it is in radian measure, your axes have to be in radian measure. You have to draw it and say it's in radian measure. But could we convert it to degrees to figure out what the heck it is initially? Because you guys have no idea what radians are right now, except for like 2 pi, pi over 2. Like you have the generic ones, but you don't know that what 5 pi over 3 is, right? So we can convert these, but we still have to, even if we convert it to degrees, we still have to state radians throughout the whole entire question, because the question was in radians, right? So radians to degrees, already pop. Radians to degrees, pi on bottom. So I can go 5 pi over 3 times 180 over pi. What's 5 times 180 divided by 3? Is it 300? Yeah? So it's in the same spot that 300 would be. 5 pi over 3 is the exact same length around as 300 degrees would be. Okay? They're the same thing, just one's in degrees and one's in radians. So 300 would fall here. So we arrow around. But we label it what? 300? Was there even a 300 in this question? No. So we're going to label it 5 pi over 3. We can use the 300 to know what it is in degrees so we can draw it, but we have to state everything in radians because this question had nothing to do with degrees. Okay? This one's negative 2 pi over 3. So we have to go around in radians negative-wise. So we're going to go 0. Then 90 is the same as pi over 2. 180 is the same as pi. You will memorize these, don't worry. 270 is the same as 3 pi over 2. And then 2 pi. But what am I missing? Negative signs, right? So now we can need to convert 2 pi over 3 to degrees. So we go negative 2 pi over 3, radians to degrees, pi on bottom. So it's going to be negative 360 divided by 3, which is the same as negative 120 degrees. Negative 120 is 60 away from 80, or 30 over 90. 30 away from 90. It's going to be here. So that's negative 120, but I can't write negative 120. I have to write negative 2 pi over 3. Does this make sense on what we're drawing? Converting? Yeah. So we'll do that in a second. So the coterminals we'll deal with tomorrow because I feel like it's overwhelming, but we'll do the reference angles for now. So this reference angle was 60. We agree? This one, the first one. This one, we'll do this one actually next. We'll do the one with degrees down here. So this one is 300. So how far away is it? 60 away, we agree? So I have a reference angle of 60 again. Do you see how these two both have reference angles of 60? However, one's in quadrant 1 and one's in quadrant 4. The reference angle is the angle between 0 and 90. And it's always from the terminal arm to the x-axis, never the y. You don't ever make hourglasses. It's always bow ties. It's towards the x-axis. Okay? Now, let's go back to this one. This one was the same as 300, wasn't it? So the reference angle would be 60. We agree? So that's great, 60 degrees. If you put reference angle of 60 degrees, are they giving you any marks? No, the question was in radians. Answers all have to be in radians. Okay? If your question is in radians, your answer has to be in radians. You have no choice. But can we convert? Yes. So reference angle equals 60 degrees. Degrees to radians, pi on top, Dr. Potts. So when you reduce it, it's pi over 3. 60 is pi over 3, 30 is pi over 6. You'll memorize those as well. 45 is pi over 4. Right? So your reference angle is pi over 3. This one is how far away from the x-axis? I was at 120. So how far away am I from 180? 60. Can I put 60 degrees? No, I have to go reference angle is pi over 3. So actually every single one of these have reference angles of 60 even though they're in different quadrants. Right? Those two are just the same thing, just in radians. So your reference angle is the little angle between your terminal arm and the x-axis. It's extremely important because when we go to do solving, we're going to need that reference angle. Okay? So I'm going to give you some questions to do for homework.